Assalamu alaikum. Hello, everyone. We continue the topic of linear regression. So today we have a case study. I will also add this video to the set of recordings that I recorded for the project guidelines. So as an example here, actually, I add more content than what it used to be here in the topic itself to explain like different steps that are involved towards building a model. We will look at those, okay? So here, this example or case study is about creating a model to predict house prices, okay? So we have a number of input features. X1 is the transaction date, X2 is the house age in years, X3 is the distance to the nearest metro station, X4 is the number of nearby convenience stores, and X5 and X6 about the geographic coordinates. The X5 is the latitude and X6 is the longitude. As I said, the target variable is the house price. The target variable is Y. So the hypothesis here is that the Y is linearly related to the input features. And actually, we're going to look at the correlation matrix as well as the scatter plots to validate that hypothesis and see if that holds in reality or not. Okay. So, but anyways, we're going to build a linear regressor for this problem. Okay. So let's look at the data here. We are loading the data. As we can see, there are no missing elements and all of the attributes are numerical attributes. So I will assume there's no any inconsistency issue. So then I will go to the next step, which is normalization. So I have chosen to perform Z-score normalization for this problem. Okay, so this is now the normalized attributes, and then we look at the correlation. Okay, we look at the correlation matrix as well as the scatter plots to come up with the full conclusion. And just one thing I want to mention here, last time I said the heat map plots the absolute of the correlation. In fact, it plots the exact value, not the absolute, okay? So here, for when we are looking at the correlation, so we want the attributes to be more correlated to the target variable and less correlated to each other. More correlated to target variable, that means there is dependency. The target variable dependent on this, the value of the target variable depends on the values of these input features. And less correlated between the features because actually we want every feature is adding something to our information. So every feature is like looking at different perspective, okay? We don't want redundancy because if there is a lot of redundancy, then that's actually, in fact, if there is a redundancy here, if there's so much correlation between different attributes, then there is a room for regularization, and then we need to introduce regularization there. So we systematically actually kill some of the features or bring their weights to be low and avoid any problems like overfitting and so on. Okay. But as I said, looking at the correlation is not enough. You need also to look at the scatter plot, and I will explain why. So let's look at here X1 and X2. Okay, X1 and X2, the transaction data and the house age, they look actually uncorrelated. Okay, very weakly correlated, or I would say uncorrelated to the target variable Y from these numbers. But it's not enough to just infer that from these numbers because, as I said, correlation coefficient, the persons are correlation coefficient can capture the linear dependency, but it may sometimes fail to capture the nonlinear dependency. Okay, so then you need to look and see if there is nonlinear dependencies. If there is nonlinear dependencies, then you may need to go beyond linear regression. You may actually consider like building higher degree polynomial features based on this in order to capture that nonlinear dependency and go beyond linear regressor. I would say for the level of 291, we're not going beyond linear regressor, but I'm explaining things in general here, okay? So it's good to look at both the correlation coefficient as well as the scatter plot. Because as I said, for example, let me just take you very quickly, okay, to this example here. The one we had at the very beginning here. So here, I'm this is a variable. It's actually I generated that. It's with like using a normal distribution with mean 0 and standard deviation 1. This is a random. These are random generated values. But actually, let's look. Give this. Let's say this is x and this is y, and I want to build like a regressor between x and y. Okay. So y here is nothing but the square of x, actually. As you can you clearly see here, the quadratic relationship, okay? So y is the square of x, okay? Y is equal to x squared. And as you can see here, in the negative side, y decreases as x increases, and in the positive side, it increases, okay? Following the, as I said, the quadratic shape, okay? So if you have looked only at the correlation, the value of the correlation coefficient between these two, you will infer or you will conclude that they are uncorrelated or they are unrelated to each other, okay? Because you are looking only at linear dependencies. So that you will infer, you will come up with a conclusion if you have looked only at the correlation coefficient that these two variables are not related to each other. But actually, there's a very strong relationship here. This is the square of that, and a perfect square, okay? So then it's good you look at the scatter plot. If the value, after you look at the value here, you look at the scatter plot. They might be uncorrelated at all, as we will see later on in our current case study. That could be like a correct conclusion. So they are unrelated at all, but there could be nonlinear dependency that wasn't captured using the correlation coefficient. So then we need to look at the scatter plot. And here we see like there is nonlinear dependency. Then maybe I need to actually consider, as I said, going beyond linear regression. Okay, in general, this is very perfect one, but sometimes you like find like there is an error. It's an average quadratic relationship, and you want to build a regressor. Then your regressor will be a nonlinear regressor will be better than linear regressor in estimating and relating these two variables to each other. But sometimes actually correlation coefficient can capture even nonlinear dependencies. That depends on two things: on the range of the values and on the function itself. For example, here, take this attitude and attitude square. Okay, this is nothing but the square of that. The function is same for both. The relation is same. Here, this was the square of that, and the correlation coefficient was very low. And here, this is the square of that, but the correlation is very high. Why is that? It's the range of the values. Here, the values are centered around 0, as I said. In the negative side, the relation is decreasing. The y decreases as x increases, and in the positive side, as x increases, y increases. So in fact, if you like regenerate those values randomly again and again, and as the number of times you generate, because they follow normal distribution with mean 0, right? If I keep generating them again and again, and every time I compute the correlation coefficient, as the number of times I generate goes to infinity, the expected value of the correlation coefficient will go to 0, okay? Because here it's a little bit biased towards the negative side, because we have generated more negative sides, negative values than positive, okay? So, but again, this will show very low correlation. But this one here, if you look at the attitude, all the values are at the positive side. So at the positive side, as x increases, x squared increases as well. So that's why we were able to capture that there is a strong relationship between them, and it's a positive relationship. So again, this also tells you, like, when you see very high correlation, maybe that is not due to linear dependency. You have to look at the scatter plot to see if it's a linear dependency and you build a linear regressor in average, or it's non-linear dependency. Then maybe I need to consider from my input feature, I need to create another feature that can approximate the relation in a better way, okay? So that's the idea behind looking at both the correlation matrix as well as the scatter plots in order to come up with a conclusion about like the linearity in do you go with linear regressor or beyond that? But for this course, as I said, we're going to assume we're going to work with linear regressors. But if you want to make it more interesting, these are the things you need to look at, okay? If you feel like the relation is not really linear and you want to go beyond linearity, that's fine. You can work on that in your project, okay? That will make it more interesting. So now let's look at the scatter plots to confirm our findings here, or to see if these finds make sense, or there are, as I said, yeah, maybe this is not what we have concluded from by just looking at the correlation may not be correct, okay? Let's look at this here. Let's focus at the last row here. This plots the correlation between the target variable and every input feature. Now, this is the first scatter plot is the correlation. This plots the scatter plot. Okay, the scatter plot between the target variable and every input feature. So here, the first one is the scatter y versus x1. Here we clearly see that they are uncorrelated actually. So this confirms our like the results we got from looking at the correlation coefficient. How did we know that? In fact, for any given value for x1, y seems to take any random variable. There's no pattern here. Okay, so for any given value for x1, y can take randomly any value. So there's uncorrelation. There's clear uncorrelation here. The same applies to x2, y versus x2. Okay, we clearly see for any value for x2, y can take randomly any value. There's no pattern here. Okay, so then these two features are uncorrelated to the target variable. This one is an interesting one. Okay, there is a relation here, but the decay, as you can see here, the decay is faster than linear decay. Okay, so this is more of an exponential decay. So if you want to make it interesting, then you need to consider maybe from this feature you build another feature that is some exponential form of this original one. But for now, for ISE 291, we will assume like it's a linear decay. Okay, but again, this is much faster than linear decay. This is more of an exponential decay, but we will assume that's a linear decay. And in fact, it's if you look at the number here, okay, and another thing, that's an average, right? There is a variance here. Okay, that's why the correlation is like, yeah. So that's I don't want to. Yeah, that's it for this one. Let me look at this one. Okay, here. Okay, for this one, we are plotting again the scatter plot of the target variable versus the fourth input feature. In average, there is linear dependency in average. As x increases, y increases, but there is also high variance. Okay, there is also high variance. So there is correlation, but not very strong correlation, as you can see here. And that's actually captured here. If you look at the fourth one here, okay, so it's 0.57. There is correlation, but it's not very strong, but there is correlation. Same applies to this and this. In average, as x increases, x5 increases, y increases, okay, in average, but there is high variance. That's why we see like there is correlation. It's not very strong, but there is correlation. Same applies to this. Here. Maybe this after some point starts to decrease, okay, but let's assume, yeah, up to here, it's in average, it's increasing, okay. And when I looked at this, I found some outliers. Then I decided to plot the box plot for the target variable. And actually, I found there are some outliers. So then I removed them here, and I just replot the figures. The conclusions are the same. I just removed the outliers, but the conclusions for every one of them is the same. Okay, I also, yeah, we don't need to look at the correlation again. Here we come to the step where we actually, now I will create different regressors following different strategies. Okay, I will build different ones. So that's why I copy the data frame to DF2. This is a new one where we're gonna build the first set of regressors based on some methodology, and then we're gonna also introduce other methodologies later on. Okay, so we split our data into training and testing subsets. Okay, so where we actually give 30% of the data, we leave 30% of the data for testing, and we use the remaining 70% for training. Okay, after, of course, like we define the x and y. X is all input features, so we are dropping the last column, which is the target variable, and we start here in y. So these are like, this is the set of input features, and this is the target variable y. After we define them, we split our data into training and testing, where we leave 30% of the data for testing, and we will use 70% for training. So here we pass this random state constant. So every time we run this again and again, like the same selection will happen. I mean, because the assignment to testing and training is happening randomly here. So if I now, with this random state constant, every time I run this again, the sample that has been assigned to the testing data set the first time will always be assigned to the testing data set. okay? So just to make sure like to maintain the reproducibility, okay? So then here we are building models, okay? We are building models based on the like OLS, okay? We have talked about that, so we don't need to explain it again. We build a regressor using OLS method, and then we test it in our testing data set. For Ridge and Lasso, we are importing Ridge CV and Lasso CV here, Ridge with cross-validation. So we pass a number of choices for our hyperparameter alpha, and we're gonna validate them in the cross-validation, using cross-validation data set. Here we're using 10-fold. We follow the K-fold algorithm. I have explained it in the past. So here in this line, what we are doing, we are training as well as cross-validating. We're training our model parameters. We're training our model parameters, and we validate our choices for the hyperparameters. Eventually, we will converge to we will actually converge to the best set of the model parameters as well as the best choice for the hyperparameter alpha. Then we test it in our testing data set, and we report the generalizability error. Okay, we import here from scikit-learn metrics, we import mean square errors. So we will use the mean square errors to the value of the mean square error on the testing data, which is the generalizability loss or error, to compare all of these algorithms. Okay, we do the same for Lasso. Okay, so here there's only one extra argument here we pass for Lasso, random state equal to 0. This actually something that's used by the algorithm that's running behind the scene to compute the solution for Lasso, because in Lasso we don't use a closed form solution and we don't use gradient descent. Okay, so now we're gonna look at what we get from running all of these different choices for the regressors as well as the hyperparameters. As you can see here, okay, so interestingly, Ridge has achieved the minimum error, okay, and actually we can, okay, these are the parameters that the best model and coefficients, okay, sorry, the best hyperparameter alpha and coefficients for Lasso, not for Rig3 is for Lasso. Okay, let's look at the ridge here. This is the ridge. Okay, so now the best choice for hyperparameter is 10. That's the one that achieved the minimum mean square error. And here are the model parameters. Okay, here are the model parameters. As you can see, the weight for the first one is very low compared to the second one. The second one is also should be low, but it's not as low as we expected here. This one was negatively correlated, and this has the strongest correlation compared to the other features. If you remember, this is like how close the house to the metro station, and it makes sense like that the correlation is negative here, right? Between the price and the distance to the metro station, because people tend to prefer to live nearby train stations, right? So that's why like as that distance increases, the price of the house decreases. Okay, and same thing, yeah, here this is the number of convenience stores. So if there are more stores, then it makes sense like this to be like more stores, that means higher price. So that's why the correlation is positive here. Okay, so anyways, let's go back to this here. So this is what we got for the ridge regression. So 10 alpha, because remember here alpha is going from what? 0.001, 0.01, 0.1, and 1, 10, 100, 1000. These are the choices we pass to alpha, for alpha, okay, to cross-validate the algorithm on them, okay? So now we found like when alpha is equal to 10, here, let me go back to this here, where was it? Here, alpha equal to 10, ridge regression with alpha equal to 10 achieves the best performance, and this is the best, like this is the model. We converge it to that model. Okay, now because this range was like was so high, I mean the differences are so high, then I went around 10 here And so is 10 the best, or I can, if I look into the neighborhood of 10, can I come up with a better choice for alpha? And this is what I did here. I started from 7 to 20, and I run again, and I actually found at 13, yeah, at 13, I achieve the minimum mean square error, 0.374, and these are the coefficients, okay? Now I build another model here where I manually dropped the first two features. Okay. So, and see, like if I drop them manually, okay. As I said, regularization can actually systematically do that if necessary. Now I dropped them manually and I built another model. Okay. And in fact, the error wasn't, though they look to me that they are very uncorrelated to the target variable, but I wasn't able to achieve better results. Okay. And if I drop, I would say I would go with all less. Okay. But I tested all of them anyways, and I didn't get better results here, lower mean square error. Maybe you can also take it as a homework. Try ridge, for example, with other choices for alpha, another range, and see like maybe you can get something lower than this. Okay. I also built another model using I computed like I tried to compress the features using PCA, okay, and I compressed them to 4 features. They cover almost 90% of the total variance. Okay, I considered only the top 4, and I also built a model based on that, but also the results were not better than what we achieved using ridge regression with keeping all the features, not dropping not dropping any of them. Okay, so with that, yeah, that's it for the example. So yeah, just to mention something here, when you're working with high data, okay, so then when it comes to gradient descent, okay, one, as I said, well, as we have studied gradient descent at the beginning, one way is to run what we call batch gradient descent, where you're using all of your data samples to compute the exact gradient at every iteration. But as the number of data samples grows very large, this will become computationally expensive. You cannot use all of your data to compute the gradient at every iteration. That will come at very high computation cost. So the extreme case is to consider only one sample when you're computing the gradient at every iteration, and that's called stochastic gradient descent. Okay, but you can also that's the extreme case. Okay, you can actually perform mini batch gradient descent, where actually you divide the data into small batches, mini batches, and at every iteration you compute the gradient like based on one of these mini batches. Or you can actually consider stochastic mini batch, where at every iteration you pick randomly n samples, okay, randomly, and you compute the gradient, the stochastic gradient in that case, okay. When you are randomly selecting one sample or a number of samples, what you are computing is called stochastic gradient, okay. So you compute the stochastic gradient using a mini batch of samples that is randomly selected. So yeah, with that you can compute the stochastic gradient and then perform what we call stochastic gradient descent algorithm. So with that, I come to the end of this topic, and I would like to thank you for watching and see you next time. Assalamu alaikum.